Hi everyone, welcome to another CNCM lecture. Today we're going to be looking at orders and primitive roots, and my name is Eli Park. So first, let's define orders. So for relatively prime integers a and m, the order of an integer a mod m is the smallest positive integer x, such that a to the x is congruent to 1 mod m, and this is denoted as x is equal to ord of sub m of a. So, if you're not familiar to orders, this may seem very weird to you, this definition. So, to get a little familiar to this, let's look at a quick example, okay? So, it asks, what is the order of 3 mod 11? Well, using our definition, we know that the order of 3 mod 11 is the smallest positive integer x, such that 3 to the power of x is congruent to 1 mod 11. So we can just probably brute force this. Plug in random values of x and see which one gives us 1 mod 11. So we'll just start at, so we'll make a little table. So this is, I'll just overlap this text right here. So I'll put x here and then 3 to the x mod 11. And then for x is equal to 1, 2, 3, let's test these for now. So we know that when x is equal to 1, 3 to x is 3. When it's 2, we have 9. And when it's 3, we have 27. But remember, we're going in mod 11. So we want to replace this with its mod 11 counterpart, which is 5. And then we see that none of these are equal to 1. So we keep going. So when x is equal to 4, we get that this is 15 mod 11, which becomes 4. And then when x is equal to 5, we get 4 times 3 is 12. Mod 11 is 1. So we see that we have 3 to the 5 mod 11 is congruent to 1 mod 11, and none of these other ones for smaller values of x is congruent to 1 mod 11. So we see that our order is equal to 5 because 3 to the 5 is congruent to 1 mod 11. So our answer is 5. Yep. So now let's look at our main theorem of orders. This really gives it's at the heart of most problems involving orders. So let's read it. For relatively prime integers a and m and integer n, a to the power of n is congruent to 1 mod m if and only if the order of a mod m is it divides n. So this is a two-directional problem, and we want to prove it because this gives us a good understanding on how useful orders are. So let's first prove the direction where we assume this is true, and we want to prove that not including the n weird and the n weird part right there. So yeah. So by definition of orders, we can well actually by this condition, what we can do is that we can let n is equal to k times the order of a mod m for some positive integer k. Let me make that a better k right there. So we can assume this, and now by and then so by definition of orders, we can also write this equation: a to the power of the order of m of a mod m is congruent to 1 mod m, and this is just a definition of orders. Well, and we want to manipulate this equation to somehow get that. So you know what? I'll rewrite some of this so we can save some space. So I'll put that up there, and we can and I'll rewrite this: a to the power of ord of a is congruent to 1 mod m. And then so we know that raising both to the kth power, or both sides to the kth power, doesn't harm the state of equality. And we know that 1 to the k is obviously k, so we just ignore the exponent for now. But we also know by our exponent rules on the left-hand side that this just becomes k times that. And we see that that's exactly that. So we replace this with a to the n is congruent to 1 mod m, and that gives us exactly what we wanted. So we have proved the first direction. So now we want to prove the other direction. And the other direction assumes this, and you want to manipulate that somehow to get that. So this is a little bit more complicated, but what we want to do is first, let's let n is equal to k times the order of a mod m plus r. And r is going to be the remainder when you divide n by the order of a mod m. So which means that r is in this range from 0 to n, where 0 is inclusive and is not inclusive, because it's the remainder when you divide it. Excuse me. We want to prove that r is equal to 0, which is basically this statement right there. So now let's go about proving this. So we're given a to the n is congruent to 1 mod m, and we can replace this with our definition of n. Let's make that look like an n. A to the power of k times order of a mod m plus r is congruent to 1 mod m. Using our exponent rules again, we can erase this r right there, and we can replace it with, oops, did not want a highlighter, a to the r. So these are multiplied. And we know that this part right here is going to have to equal 1 mod m, because a to the order of m of a is congruent to 1 mod m. So we'll replace it all with a 1. We'll replace this with a 1. And replacing it with the 1 basically does nothing, so we're just left with this. We're left with this statement. Well, what does this tell us? This looks eerily familiar, and this looks a lot like our definition of orders. If you remember, you look back here, a to the x is congruent to 1 mod m. But then you're thinking, wait, so that means if, for example, if r were positive, if r is positive, this gives us a contradiction, because we know that the order of a mod m is the smallest positive integer, such that a to the x is congruent to 1 mod m. Replacing x with the order up here is the smallest positive value of that. But then we know that r has to be less than the order of a mod m. And it has to be less than that, because that's the definition of, by definition, of remainder after division. So r can't be positive here. And that basically only leaves us with one option left. And that means, since r can't be negative, because by remainder has to be non-negative, we have that r is equal to 0. So if we make this r 0, then we can basically erase this up here. And we get the n is of the form k times the order of a for some positive integer k, which implies our desired statement right here. So let's look at a corollary. This is also pretty important. For relatively prime integers a and m, the order of a mod m divides phi of m. Well, given that we've already proved this previous theorem, this is actually kind of easy, because by Fermat's little theorem, we know that a to the let me write in black. We know that a to the phi of m is congruent to 1 mod m. And then earlier we said that we had this there, we had that. So we can basically just replace n with phi of m. And then this gives us our statement: order of m of a divides phi of m, which is exactly what we wanted. And then in the case where m is replaced by a prime p, this becomes order of a mod p divides p minus 1, because that's how phi works with primes. So now let's look at some examples, because the best way to learn is with examples. So our first example is the 2019 AMY 1 problem 14. It says find the least odd prime factor of 2019 to the 8th power plus 1. So we first let p be a prime such that an odd prime specifically that divides 2019 to the 8th power plus 1. So we can write the statement that 2019 to the 8th power is congruent to negative 1 mod p. And then squaring both sides, we get 2019 to the 16th power is congruent to 1 mod p. So this statement right here gives us that the order of 2019 mod p divides 16. Because and that gives us that it divides 16. Because if it weren't, then it's not possible for this statement to be true, because it has to be some power of the order. But then we also have here that we have this statement, and this basically gives us that the order of p to 2019 is not equal to 8, and it's not any of 8's divisors, because since p is not 2, this is not equal to 1 mod p. So this means that the order of 2019 mod p is equal to, not just divides, is equal to 16. And this gives us a whole lot, because by our theorem, our previous theorem right here, we see that the order of 2019 of p divides p minus 1. But we know that the order, we can replace this with 16, and this helps a lot. So now we've deduced a lot of information here. Let me erase a lot of this stuff that we have right here. We've actually gotten a lot of information now, because this tells us that p is congruent to 1 mod 16, and there's actually and there's actually not that many primes of this form. Well, the first prime is 17, so we can try to evaluate 2019 to the 8th power plus 1 mod 17. So division gives us that this is congruent to 13 to the 8 plus 1 mod 17, congruent to 169 to the 4th power plus 1 mod 17 is congruent to negative 1 to the 4th power plus 1 mod 17, which is congruent to 2 mod 17, which is not equal to 0, which means that 17 is not a prime factor here. So we go on to the next one. Remember, p is congruent to 1 mod 16. Next number is 33, not a prime. 49, not a prime. 65, not a prime. 81, not a prime. 97, that is a prime, so we'll check that now. We'll try to evaluate 2019 to the 8th power plus 1 mod 97. This is just basic modular arithmetic right here. Nothing special. So this becomes negative 18 to the 8th plus 1, which becomes 33 to the 4 after you square that, plus 1, which becomes 22 squared plus 1, which becomes 485. This is all under mod 17. And we see that 485 is equal to 5 times 97. So indeed, this is congruent to 0 mod 97, which verifies that 97 is a prime factor of 2019 to the 8th power plus 1. And we've, by our process, have checked that this is the smallest prime factor of that. So our answer is 97. So let's look at another example. So this is a classic. So prove for all integers n greater than or equal to 2 that n does not divide 2 to the n minus 1. So the idea here is first we want to let p be the smallest prime factor of n. And we know that this has to exist because n is greater than or equal to 2. So now, for the sake of contradiction, we want to assume that n does divide 2 to the n minus 1. This is for the sake of contradiction. We know that p, and this gives us that p divides 2 to the n minus 1. This should be direct, which gives us 2 to the n is congruent to 1 mod p. And this gives us, this is looking a lot more like our standard orders, which starts to give us that order of 2 mod p divides n. And then our theorem 2.1 also tells us that order of p of 2 divides 5p, which is p minus 1. So this is interesting now because let me give some divides to make this stand out a little better. So this is interesting now because we start to think about this and so hey, the order of 2 mod p divides n, so that must be a divisor of n. And we can look down here, so that divisor of n also divides p minus 1. But that doesn't make sense because this bottom one implies that the order of p of 2 is less than or equal to p minus 1. But then we assume that p was the smallest prime factor of n. So that doesn't make sense. This is a contradiction here. Oops, sorry. This is a contradiction here because there cannot be any divisor of n smaller than p, but clearly the order of 2 mod p is smaller than p. So this gives us a contradiction and our statement is never true. So now let's look at one a little more complicated example. This will get into a little bit of casework. So let's first read it. This is from Bulgaria, 1996, round 4, problem 1. Find all pairs of primes p and q such that pq divides 5 to the p minus 2p times 5 to the q minus 2q. So we know that either p, so we're going to start dividing this into cases, but we know that since p is prime, it has to either, if it divides, it can divide 5 to the p minus 2 to the p. But if it doesn't, then that means that it has to divide 5 to the q minus 2 to the q, or else there's no way for p to divide this quantity right there. And then and we also have the similar for q. So we can basically divide our problem into 4 cases where first case is where this and this is true. The second case is where the second and third cases is where only one of them is true, and then the fourth case is going to be where none of them are true. And then when none of them are true, that obviously implies that this is true and this is true. So let's look at the first case where both are true, meaning p oh my gosh, oops, sorry, where p divides 5 to the p minus 2p, and the same goes for q. So let's investigate this, which gives us that 5 to the p minus 2 to the p is congruent to 0 mod p. By Fermat's little theorem, we get 5 to the 1 minus 2 to the 1 is congruent to 0 mod p, which gives us that p has to equal 3. There's no other p that works. And then this goes the same for q. So we get that in our first case, we have a pair, p and q are equal to 3. So we'll log that on our next page here just for safekeeping. So now let's assume that p divides 5 to the p minus 2 to the p here, but assume that q does not divide 5 to the q minus 2 to the q. And this implies that q divides 5 to the p minus 2 to the p. Well, this obviously, by our earlier result, gave us that p is equal to 3, which means that this has to become q divides 125 minus 8, which is equal to 117. This gives us that q has to, this gives us that q is equal to 3 or 17. And then, so this gives us the pair 3, 3, and 3, 17. And since we already have 3, 3, we'll just write 3, 17. Wait, hold up. That should be 3, 13. My bad. I tried attempted division in my head. Doesn't work anymore. Yeah, and our other cases also symmetric because our other case where we replace each instance of p with q here, meaning that this becomes q, and we replace these with p, and then we replace this with p, q, 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 p, and yeah. And this is our other case where only the statement is true for q, and this gives us that q is equal to 3, and then this leads us to p is equal to 3 or 13, so that gives us our other one, 13 to 3. So now our finale case is where where p divides that and not this, and where q divides that and not this. So let's see what this gives us. Let's first look at this. 5 to the q minus 2 to the q. This gives us that 5 to the q is congruent to 2 to the q mod p. And then dividing by 2 to the q mod 2 to the q on both sides gives us that 5 times the inverse of 2 mod p, all to the q power. This is not a 9, remember that. Congruent to 1 mod p. Well, you may have been wondering while I was doing this problem, where are we using orders? Well, we're finally using orders here now. So, we're finally using orders here. Let's actually for now we'll just go ahead with this. So this gives us that the order of 5 times 2 to the negative 1 mod p divides q. But since q is prime, this means that this has to equal either 1 or q. So let's say, for example, that it was equal to 1, okay? Then that means that this statement is also true then. 5 times 2 to the negative 1 to the 1th power is congruent to 1 mod p. But this is the same as 5 is congruent to 2 mod p, which gives us that p is equal to 3. And that's not particularly useful because we've already found all the pairs where p is equal to 3. So now that means that we can just assume that our only possibility for the order of 5 times 2 to the negative 1 mod p is q. So I'll make this a little clearer by writing it on one line. And then and we also know by our theorem that this divides 5p, which is equal to p minus 1. So our conclusion is that q divides p minus 1. But the thing is that we can do the same exact work on the other hand, where we switched p and q around. This gives us that p divides q minus 1. But this is absurd because this implies that q is less than p. This gives us that q is less than p minus 1, and this gives us that oh my gosh, what am I writing? This gives us that p is less than q minus 1. And this is not necessarily absurd yet because, actually, yes, this is very absurd. My bad. Because, and this gives us that no pairs, other pairs for this case. So these are our 3 pairs and we are done. Answer there. So now we're going to roughly go over primitive roots. We're not going to go into them very in depth, but let's define them for now. So let g and m be positive integers. We say that g is a primitive root mod m if the order of g mod m is congruent to phi of m. So there exists, our theorem here for primitive roots is that there exists a primitive root mod m if and only if m is equal to 1, 2, 4, a power of p, or 2 times the power of p. The only particularly useful case, well, not actually necessarily, but most of the times a particularly useful case is where m is just equal to p, because it's just a lot more simpler. So as an example, we want to find a primitive roots mod m. So if we remember our definition, if we remember our definition, we want to find the order of 1, 2, 3, and 4 mod m. We don't want to find 0 because this is not relatively prime to 5. Everything has to be relatively prime here. So we want to find the order of 1, 2, and 3, and 4 mod 5 and find which of them is equal to, which of their orders is equal to phi of 5, which is equal to 4. So we'll just list, this is routine exercise. The order of 1 becomes just 1, 1, 1, etc. So the order is just 1. 2 becomes 2, 4, 3, 1, which gives our order is 4. 3 gives 3, 4, 2, 1, which gives our order is 4. And then 4 gives us that 4, 1, which means our order is 2. So we get that 2 and 3 are 2 primitive roots of 5. Let's look at example 4. Prove that if p is a prime such that p is congruent to, this is going to be our last example, by the way. This is a pretty cute example. So prove that if p is a prime such that p is congruent to 1 mod 4, then there exists a positive integer a such that a squared is congruent to negative 1 mod p. So our statement here implies that a to the 4 is congruent to 1 mod p, because we can just square both sides. So recalling our definition of primitive roots, we know that if g is a primitive root, then g to the p minus 1 is congruent to 1 mod p. So this gives us a little bit of becomes interesting because we could try to directly just plug this into here somehow. By plugging in a is equal to g to the power of p minus 1 all over 4, we get that this statement becomes g to the p minus 1 over 4 to the 4th power is congruent to 1 mod p, which gives us that g to the p minus 1 is congruent to 1 mod p. So this statement is indeed true, which gives us a little bit of hope now because it looks like this construction may actually work because it satisfies an implication of the given equation. But this is actually this doesn't actually finish the problem. We still have to check that that this substitution in red right here actually satisfies our given equation. So let me erase this right here and let's try to plug in and see what it gives us. Plugging it in, plugging it in gives us that g to the, let me write it in black. G to the p minus 1 over 2 is, so we want to verify that this is not equal to 1 mod p, because if it's not, then this implies that is equal to negative 1 mod p by squaring it. Well, how can we prove that this is not congruent to 1 mod p? Well, if the above were congruent to 1 mod p, then we would have a contradiction, because by definition of primitive roots, we have that the order of g mod p is equal to p minus 1, not p minus 1 over 2. And since we have, that means that this statement cannot be true, because p minus 1 is the smallest exponent that can be put here. That makes this equation true. So we have a contradiction, meaning that g to the p minus 1 over 2 is not equal to 1 mod, not congruent to 1 mod p, and this implies our given equation. So that's it. Thank you for listening to my lecture, and be sure to join CNCM if you haven't already joined. Thank you, and see you next time.